In this video, we're going to take a look at Newton's universal law of gravitation. So Newton had the realization that the force of gravity of the Earth and things near the Earth is actually the same force of gravity that acts between objects throughout the universe, which is kind of a big jump when you think about it. The force of this apple that supposedly fell on his head is the same force that pulls the moon towards the Earth towards the sun, and so forth. So let's take a look at an example. We're going to take a look at an example where we have the sun here. So this is the sun, and a person near the Earth, and we want to find out what force the sun applies to the person. So the Earth is right here, so the person on the Earth. We can figure out how much force the Earth applies by using mg, okay? But we want to find out how much force the sun applies to that person, this force right here, okay? So we want to find the force of the sun on the person, okay? And we need to know some numbers here, so let me throw some numbers out here for you real quick. The mass of the sun is equal to 1.99 times 10 to the 30th, which is a pretty large number, 30th kilograms. So we need to know the mass of the sun. We'll say this person for this example is 90 kilograms, a 90 kilogram person. And we also need to know the distance between the two objects. So the sun-Earth distance, and I'll use right here is the distance here. It's actually to the center of the Earth, but it's 149.6 times 10 to the 9th meters. So it's 149.6 billion meters away. Most people know it as the 93 million miles away. Okay, but in meters it's 149.6 billion meters away, which is pretty far. So we want to find the force of the sun on the person. So the equation is F is equal to, this is the equation you develop, G, which is a universal gravitational constant, not little g, which is our 9.8 we use on Earth. This is a number that's used everywhere in the universe. The mass of the first object, mass of the second object, okay? And it doesn't matter which is which because they're just multiplied, so it doesn't matter the order you multiply with. Divided by the distance squared. So this is the r value, radius, the radial distance, or how far they are apart. So we need to know the masses and how far apart they are. So I'm going to list the variables here. Step 2, F, big G, M1, M2, and R. Okay, so force we don't know. We're trying to find the force, so I'll leave that blank here. Although we do know the unit of force is in newtons. Forces are always in newtons. Okay, big G. Now big G is the universal gravitational constant at 6.67 times 10 to the minus 11. So you know this number all the time. Okay, and it's in newtons meters squared divided by kilograms squared. Okay, mass 1, I'll say it's the sun. Again, it doesn't matter the order because we're just multiplying, but I'll say it's the sun. It's 1.99 times 10 to the 30th kilograms. And the mass of the second object, the person we're talking about here, is 90 kilograms. And the distance between the two is the 149.6 times 10 to the 9th meters. So billion meters away times 10 to the 9th is billion. Okay, so solving is just a matter of plugging in the numbers correctly and really making sure our exponents are correct. So it's F is 6.67 times 10 to the minus 11th times 1.99 times 10 to the 30th, it's a big number there, 30th, times the mass of the person, or the other mass is 90 kilograms, and the distance between them is the 149.6 times 10 to the 9th squared. So a lot of this is going to have to be making sure your exponents are correct on your calculator, although I'm going to show you something here in a second that will simplify it. If you do all the math here, you're going to get 0.533, that's a 33 newtons. Okay, so it's actually just a half a newton. It's not actually not a lot of force. The mass of the sun is pretty large, but it's so far away, the force is almost negligible. Just for comparison's sake, if I use mg for the Earth, it's a 90 kilogram person, and g is 9.8. I'll round to 10 just for simplicity. It's about 900 newtons. So the Earth actually applies a lot more force than the Sun because the person's right near the Sun. The Sun does apply a force, but it's so far away that it's almost minuscule. It's half a Newton, okay, which isn't a big deal, okay. Start to move the person away, and the distances change, and the effect of the Sun will become greater. So let me take a look at a slightly alternate way of solving this that involves some rules from algebra and exponents. So we have these really small numbers times 10 to the minus 11th and really large numbers. So the exponents can kind of make the calculations a little bit harder than they have to be. So I'm going to use the rule where I can take exponents and add them if they're multiplied like these two are, and subtract them when they're divided like these are. Okay, so I'm going to rewrite this. This is an alternate method. I'll get the exact same answer. I'll take 6.67. I'm going to take that 1.99, and I'm going to take that 90. I'm not going to put any exponents in here. But I'm going to say that times 10 to the 11th and times 10 to the 30th, they're multiplied. So I just add those. So 30 and minus 11 is times 10 to the 19th, because 30 minus 11 is 19. So I'm just taking care of those two right there. Then I'm going to divide by that 149.6, and it's squared. But also this times 10 to the 9th is squared. So 10 to the 9th times 10 to the 9th is really times 10 to the 18th, because I'm adding the exponents. Okay. And then check this out. I have these guys that are divided. So when I divide, I can subtract exponents. 19 minus 18. So this really becomes, these two become times 10 to the 1. 19 minus 18 is 1. So in your calculator, you actually only have to type these guys in. Times 10 to the 1, which is just basically 10. So if you multiply 6.67 times 1.99 times 90 divided by 149.6 squared, and then multiply by 10 to the 1, you're going to get the exact same answer of 0.533 newtons. So that's putting the rules of exponential addition and subtraction to work, and makes life a lot easier when you're calculating, and you will get the exact same answer. Okay. So in the big scheme of things, Newton saw that, or had the realization, and he proved quantitatively that the forces between objects depend on the mass of the first object, mass of the second object, and how far are they apart, along with this gravitational constant. So if I know those quantities, I can solve for the forces of any two objects, or any 3 or 4 or 5 objects in the universe. And this is the equation that astronomers and physicists use and engineers use to analyze the motions of planets and things in the universe. So that's an overview of Newton's universal law of gravitation.